In this chapter, we address the terminal digital twin scoping problem. The question is not whether a digital twin is useful, but what to include first when budget, time, and organizational capacity are limited. A good scope becomes a decision tool that improves throughput, reliability, and cost. A bad scope turns into a high-maintenance system that is too complex to operate, so it delivers little value despite high investment. Scoping is hard because full digitization is rarely feasible. Every additional component adds sensing needs, data pipelines, integration work, governance overhead, and ongoing maintenance. The critical discipline is to prioritize what creates the largest operational leverage per dollar and per engineering hour, while avoiding the failure mode of building a broad but shallow twin that cannot be trusted or sustained. This slide establishes the operating scale for Mediterranean Container Terminal, abbreviated as MCT. It is a 2.4 million 20-foot equivalent unit facility with 8 berths, 42 quay cranes, and 180 yard cranes. The yard spans 156 hectares organized into 48 blocks. The Port Authority allocates $15 million over 3 years. A full terminal digitization would exceed $50 million and take 7 years. So a stage scoping decision is not optional. It is the only realistic path. MCT processes about 12,000 container movements daily across multiple domains. Gate operations include about 3,500 daily truck transactions, and rail operations handle 15% of total volume. Maintenance covers roughly 280 pieces of equipment. Each domain has different data requirements and different payoffs. For example, vessel and quay decisions are time-critical, while some maintenance analytics can tolerate slower batch updates. Scoping must reflect these differences. This chapter uses 4 tiers. Tier 1 is a complete mathematical baseline that selects which components to digitize and which sensors to deploy under constraints. Tier 2 is a practical, greedy heuristic that produces an explainable initial scope quickly. Tier 5 expands to a system of systems integrated digital twin, and Tier 7 focuses on a human and artificial intelligence partnership, where explainable recommendations are refined by operational judgment. Tier 1 frames scoping as a selection and coverage problem. You choose which terminal components enter the digital twin, and you choose sensor locations so every selected component is observable. The model explicitly balances operational value against digitization cost, sensor cost, and complexity. It also enforces real constraints like budget, staffing capacity, and dependencies between components. This slide defines the sets and the key inputs. There is a set of candidate components, such as equipment, processes, and areas, and a set of sensor locations that can cover them. Operationally, this is where many projects go wrong. Teams list components to digitize, but do not define the sensing plan. This tier forces you to tie scope to measurement, so the twin can actually be built and validated. The decision variables are binary selections. One variable indicates whether a component is included in the digital twin. Another variable indicates whether a sensor is installed at a specific location. This structure creates a clean link between scope and sensing. If a component is selected, the model must also select at least one sensor location that can cover it. The objective balances 2 forces. It rewards high operational value per total spend, including both digitization cost and sensor installation cost. It also penalizes complexity because complexity drives integration time, governance burden, and long-term maintenance risk. In practice, the complexity penalty is what prevents a project from selecting an attractive but unrealistic scope that the team cannot deliver within the program window. This slide summarizes the constraint set. Coverage ensures every selected component can be monitored. Budget ensures total cost stays within the approved funding envelope. Resource constraints limit the total implementation effort. The model can also include a minimum value floor, a maximum complexity ceiling, and dependency rules. Together, these constraints turn a business wish list into a feasible, implementable scope. The coverage constraint is the feasibility backbone. It requires that if a component is included, at least one selected sensor location must cover that component. Operationally, this prevents building a twin that is blind. If you cannot sense a process or an asset reliably, you cannot simulate it accurately. and you cannot use it for decisions like scheduling, appointments, or maintenance planning. Dependencies capture real implementation logic. Some components cannot stand alone and require prerequisites. If a dependent component is included, its prerequisite must also be included. This prevents wasted investments where advanced analytics are selected without the foundational data capture, integration, or operational workflows required to sustain them. This example matrix illustrates coverage. Each row corresponds to a component, and each column corresponds to a sensor location. A 1 indicates that the sensor location can monitor that component. Use this idea to build a real scoping map at the terminal. It makes coverage gaps visible early, and it shows where shared sensor infrastructure can enable multiple digital twin capabilities. This architecture figure summarizes how the scoped digital twin is assembled from components, sensors, data pipelines, and decision services. As you view the diagram, focus on boundaries and interfaces. What data sources are required, how the twin synchronizes with operations, and what operational decisions the twin is expected to support. This concrete example uses 3 candidate components. The key crane has value 85, cost 120, complexity 3, and resources 40. The yard block has value 65, cost 80, complexity 2, and resources 25. The gate system has value 75, cost 95, complexity 4, and resources 35. With a budget of 250 and resource limit of 80, the example selects the key crane and the yard block, supported by sensors at locations 2 and 3. The reported totals are value 150, total cost 240, and resources 65. This slide explains why the objective is structured as a ratio with a complexity penalty. The ratio pushes the model toward high value per dollar, which is critical under a $15 million program cap. The complexity penalty counters a hidden risk. A scope can look valuable on paper but fail in delivery due to data integration complexity. Penalizing complexity keeps the architecture maintainable and increases the chance of adoption. Tier 2 is designed for speed and explainability. Instead of solving a full integer program, the greedy value density heuristic ranks components by value per cost and selects them while constraints remain feasible. Crucially, it also selects sensors. That means the output is a complete first scope recommendation that includes both what to digitize and what data capture must be installed to support it. This flow diagram shows the greedy loop. You compute a score for each component, sort, then iterate. When you tentatively add a component, you also add the lowest cost sensor that provides coverage, unless that sensor is already selected. This mirrors how real scoping workshops work. Teams compare options quickly, check feasibility, and prefer shared infrastructure that covers multiple needs. This code slide shows the greedy scoping function structure. Focus on the value density computation, sorting by score and the running totals for cost, resources, and value. Notice the key design choice. When a component is considered, the code finds sensors that can cover it and selects the cheapest option while avoiding duplicate sensor costs. This continuation shows the feasibility checks and the acceptance logic. A component is accepted only if both the digitization cost and any additional sensor costs still fit inside the budget. The validation helper then checks that every selected component is covered by at least one selected sensor, which prevents incomplete or misleading scope recommendations. This example code defines a realistic candidate list: quay crane automation, yard management, gate automation, rail interface, equipment maintenance, truck appointments, a monitoring dashboard, and environmental monitoring. It also defines sensor locations such as quay, yard, gate, rail, equipment, truck staging, weather, and perimeter. Read this as a scoping catalog. The goal is not the exact numbers, but the structure. Each component has value, cost, complexity, and resource needs, and each sensor has a cost and a coverage rule. This section shows how the greedy selection is executed under a fixed budget and resource setting. It selects components in priority order and adds sensors while avoiding duplicates. The printed output includes selected components, selected sensors, total value, total cost, and a value-to-cost ratio. That makes the recommendation auditable for decision makers. This part completes the example by running validation. Validation ensures every selected component has sensor coverage. In real deployments, this is where you would extend validation to include data quality rules, integration readiness, and organizational readiness for each selected capability. This continuation finishes the example, execution and reporting. The point is to show a full loop. Define candidates, run the heuristic, compute totals, and validate coverage. This is the minimum standard for scoping outputs. The recommendation must be reproducible and explainable, not just a slide with a subjective priority list. The reported greedy outcome achieves about 87% efficiency in value-to-cost ratio. The suggested initial scope includes a monitoring dashboard, gate automation, truck appointments, yard management, and environmental monitoring. Interpret this as an early phase design. Prioritize broad visibility and controllability across critical flows, while leaving heavier automation investments for later phases once the data foundation is stable. These practice questions reinforce Tier 1. You are given 8 components with value, cost, complexity, and resource requirements, along with a budget of 450, resources of 180, and a complexity limit of 12. Your task is to formulate a complete integer program and compute the optimal independent selection. This builds the skill of translating scoping discussions into a precise decision model. This slide extends practice into Tier 5 and Tier 7. For Tier 5, you design an integrated system of systems twin for a terminal handling 800,000 20-foot equivalent units annually. For delay propagation, model a 6-hour vessel delay affecting 3 vessels, 180 container repositionings, 240 truck appointments, and 1 rail slot. For Tier 7, design an explainable interface that supports conflicting stakeholder priorities. Tier 5 moves from selecting isolated components to designing an integrated system of systems twin. The core insight is that terminal performance is driven by coupling. Vessel plans affect yard moves, yard availability affects gate throughput, and rail scheduling depends on container readiness. An integrated twin coordinates subsystem twins, so decisions are optimized end-to-end, not locally within one department. This architecture figure shows how the subsystem twins connect: vessel operations, yard management, gate operations, rail operations, and equipment maintenance. As you review it, think of 2 loops: a fast synchronization loop that keeps the digital state aligned with reality, and a decision loop that runs optimization and what-if analysis across subsystems. In the Black Friday surge example, the terminal plans for a 35% volume increase over 5 days. The integrated twin coordinates changes across all subsystems instead of reacting late. Reported improvements include reducing vessel port time from 28 hours to 23 hours, increasing effective yard capacity by 18%, reducing average gate processing time from 45 minutes to 31 minutes, increasing rail share from 15% to 22%, and increasing equipment availability from 94% to 97.5%. This slide summarizes system-level metrics from the surge scenario. On-time vessel departures reach 94% during the surge versus a historical 76%. Total operating costs are reported as 12% lower through coordinated optimization. The reported incremental value is $2.3 million compared to optimizing each subsystem independently. The key message is that integration creates value beyond the sum of local improvements. Tier 7 introduces the Centaur model, a human and artificial intelligence partnership. Scoping is strategic and contextual, so the best decisions combine human priorities and constraints with data-driven analysis and scenario modeling. Explainable recommendations are central. Decision trails, sensitivity analysis, confidence scoring, and alternative path analysis help stakeholders understand why a scope is recommended and how trade-offs change when priorities change. This slide shows the human and artificial intelligence scoping architecture. Humans set objectives, risk tolerance, and constraints, and the system produces ranked scope options with explanations and trade-offs. The interaction is iterative. Humans refine, the system recomputes impacts, and the final decision becomes both analytically justified and operationally feasible. In the concrete example, the terminal manager Sarah Chen scopes an $8 million expansion. She weights vessel turnaround at 40%, maintenance cost reduction at 30%, and customer satisfaction at 30%. The system analyzes 18 months of data. It finds that quay crane delays account for 34% of vessel schedule variance, yard congestion reduces throughput by 18%, equipment failures cost $2.1 million annually, with 67% being predictable, and gate time variance correlates with container location uncertainty. These practice questions summarize what implementation readiness looks like across tiers. For heuristics, you should be able to implement and validate the selection logic. For integrated twins, you should be able to define subsystem interfaces and quantify cascading impacts. For human and artificial intelligence collaboration, you should be able to design explanations and interactive refinement workflows that resolve conflicts between stakeholders rather than hiding them. To close, digital twin scoping is a portfolio decision. You select components and data streams that must work together under budget, staffing, and complexity constraints. Tier 1 provides a complete baseline model with coverage and dependency safeguards. Tier 2 provides a fast, explainable first scope. Tier 5 shows why integration creates system-level value. Tier 7 ensures the scope is adopted by combining explainability with human judgment.